So here is a very interesting question. The question here is, okay, let me just recap what we have just discussed in the video. So this is the update function for SGD, right? So again, remember that these weights are vectors. This gradient is basically a vector gradient, right? So here, this is my learning rate, right? So we have discussed this, whether you have batch SGD or mini batch SGD or simple SGD, this is basically your update. But in the case of Agagrad, what happens is the equation looks very similar, except that this learning rate, there is one learning rate per feature, right? So there is one learning rate per weight. So I'll explain you why this confusion with weight or feature is there. I'll just clarify this confusion, right? And this is time dependent, unlike this where this is a constant that we fix. Now, one of the reasonings I gave in the course videos, which is why do we need this? One of the reasonings I gave here is if you have a sparse feature, right? I mentioned this without giving too much detailed justification. So if you have a sparse feature, it makes sense to have if you have a sparse feature versus a dense feature. Again, there is some confusion on features and weights. I'll just clarify that in this video, right? If there is a sparse feature versus a dense feature, I mentioned, I didn't give proper justification for it, but I just mentioned that if you have a sparse feature versus dense feature, having this as a constant is not very good. Now let me justify that while clarifying the confusion between the concepts of feature and weight as I describe it, right? So this is just a recap of what we have already seen in the course videos till now, right? So let's go for it. Okay, so let's look at it only from the perspective of a single activation function, just to keep our math simple. Right? Suppose if I have a weight, see, corresponding to every weight, there is an input. That input is what I'm calling it as a feature. When I say we have a sparse feature, what I mean here is, or when I say we have a sparse feature corresponding to a weight, right? All that I'm saying here, again, I'm trying to take the simplest example so that the math is simpler, right? What I'm simply saying here is the input that you get corresponding to this weight, that's what I'm calling it as feature. So when I say we have a sparse feature, all I mean here is corresponding to this weight, there is an input. That input now is sparse. What do I mean when I say sparse? What I mean is if this is sparse, most of the times it is non-existent or it's NA. Only in few cases that feature value exists. So when I say a sparse feature, what I mean here is an input corresponding to this weight I. Let's take a simple example so that it's easier to understand. Imagine if I have a single activation function here, right? And I have a bunch of weights here and there is an output and there is a loss function corresponding to it. Now imagine I have a feature I or an input I corresponding to weight Wi, and let's assume, okay, we'll talk about, so I hope this clarification about feature and weight is now resolved, right? So you got this clarification. Again, while I'm giving you the example from a single neuron perspective, this could be true even if you have multiple neurons, right? Even if you have a complex circuit like this, right? When I'm looking at it from this perspective, look at this. This output goes here. There is a weight corresponding to it. There is an input coming in, which is the output of this neuron. So if this output is sparse, right, then I would say that this feature or this weight corresponds to a sparse feature. That's all I'm saying here, right? Now let's look at, so again, remember that this is a vector equation, right? Your W here is a vector of all the weights that you have. Let's look at it only from this feature's perspective, only from that feature's perspective. Let's say I have feature Wi, right? So feature Wi at time t. Again, what I'm doing here is I'm writing the scalar variant of this vector equation, right? So again, here remember that I have the grad here. Grad is nothing but it's basically a vector of partial derivatives. So this is something that we have already discussed in the course videos. For example, if you go to this chapter, right? If you go to this chapter, which is solving optimization problems, I discuss about SGD in lots of detail here, right? So I hope you have gone through these videos. Okay, so coming back to the discussion here. So if I look at it only from this feature's perspective, let's assume Wi is a feature. So Wi is a weight which has feature I or input I on which this weight is being applied, right? So if you look at it from that perspective, again, this is just, I've just put W superscript I here to clearly say that this is a scalar. This is just one weight of the many weights you may have in your network. So weight I at time t is weight I at time t minus 1 minus the learning rate. In SGD, this is fixed. This is the partial derivative at t minus 1. Simple. Now let's assume that this feature or input is sparse. Okay, that's the case, right? So imagine if this is sparse, what happens? What does it mean? If this is sparse, which means mostly it is NS, it doesn't exist. Mostly it doesn't exist. The data doesn't exist at all, right? So, and often in most of deep learning, what we do is a mini batch based SGD. I've already mentioned this earlier. Now in a mini batch SGD, what happens? When I pick, see, look at this. What I do is typically I pick a bunch of points and I compute the derivative. I compute this derivative based on those points, right? Because if I have a very large data set, computing this derivative with respect to all the points, which is actual SGD, is very expensive. So we do a mini batch SGD, right? In mini batch SGD, what happens? In each batch, a lot of my batches will contain mostly missing values or NS and just a few valid values. Which means if I create a batch, look at this, if I have a bunch of values for this feature I in my mini batch, most of these values will be non-existent or NS. Only some of them will be valid. Now, why is that relevant here? Now let's look at the whole case where my feature I or input I corresponding to weight I is sparse. Now when that happens, my claim is this. When that happens, I'm going to claim that this partial derivative will be very small. Your obvious question is why? How can you say that? How can you say that this partial derivative is going to be very small? Right? Now, I'll give you a simple example. Again, I'm trying to simplify it so that you understand the core concept itself. Let's take a very simple example. Okay, because this is something that we've already worked out, right? Let's assume my loss is squared loss, like a typical linear regression type of problem, right? Let's take a simple linear regression. Because in our course videos, if you go to this chapter, right? If you go to this chapter, which is solving optimization problems for linear regression. So there is this video called as gradient descent for linear regression, right? So if you go to this video, I have derived step by step what is the update function, I've clearly derived what, okay.
As we discussed in the previous
so I've actually derived step by step what this partial derivative will look like. This partial derivative, again, I'm just giving you one example. You can verify this for any loss function, even for logistic regression, you can verify this. I'm just giving you, so my claim here is that this derivative will become very small. Now, why would it become very small? Let's look at it just as an example from the perspective of linear regression so that you understand the concept. When you're using squared loss and linear regression, as we have shown in this video called gradient descent for linear regression and solving optimization problems chapter, this derivative is exactly this. Now imagine, look at this. This derivative is exactly this. Now what are xi's here? Xi's are inputs, right? In linear regression, what is this feature I? This feature I is nothing but this whole thing is my data point xi, and this is one feature corresponding to my input, right? Now if this is missing, look at this. When this feature is missing, what happens? This whole value goes missing. Again, sometimes we can also represent missing values with zeros. Right? If I replace the missing values with zeros, or if I just ignore all the missing values, this whole thing will become zero for that, right? Which means for a lot of points in my mini batch, for a lot of points, because they're missing, I can represent them as zeros, right? For a lot of points, this value becomes zero, which means this summation becomes very small compared to a feature, right? Look at this. Imagine if I have two features, one sparse and one dense. For the sparse feature, because I have mostly NS, which I can represent using zeros, right? This whole derivative will become much smaller than a dense feature. Because for a dense feature, there are genuine values here, right? So what happens here? So I hope this claim is justified, that this whole derivative will become small. Again, I'm justifying it with an example because we've already derived this in the course videos, and it's simpler to understand by just looking at a single neuron or a single activation function based system. And I'm just showing a much simpler case here, just to convince you that sparser features will result in smaller derivatives, right? Now, when you have a smaller derivative, look at this. If this derivative is small, what happens? What is your update function? Look at this. What is your update function? If this is very small, if this becomes very small, because my feature or input doesn't exist, what happens? My WT at I is same as WT minus 1 at I. Look at this. So what happens? The weight corresponding to a sparse feature is not changing much. There is not much change in the weight corresponding to the sparse feature. While the weight correspond, let's assume there is another feature j, or there is another weight j. Let's assume there is another weight wj. Corresponding to it, let's assume there is feature j or input j. Let's assume this is dense. Because this is dense, this value will not be missing. Because this value is not missing, this derivative is not too small, which means your wt is not going to be same as wt minus 1. There will be some difference. So what happens if you have a dense feature? Look at this. If you have a dense feature, your wt at j is going to be different. It is different from wt minus 1 at I, which means this is changing, which means with respect, sorry, not I, j, right? Because j is a dense feature, which means with respect to feature j, we are moving towards the minima, but with respect to feature I, we are not moving much. And why is this whole thing happening? Because this number is fixed. Now, if I change it in such a way, remember, so the whole idea here is I'll change this in such a way that sparse features will have, see, the whole idea of Agagrad is this, that sparse features will have larger values and dense features will have smaller values. Right? This is something that I've also already explained in the comment section, and you can easily understand this from how we explain how to compute this whole thing. Right? So this is the idea. This is the problem with standard SGD. If you have a sparse feature, what do I mean by a sparse feature? Sparse feature basically means I have an input corresponding to which there is a weight associated. If this input or feature is sparse, which means it's mostly NS, which we can also represent using zeros, then this weight would not move much as compared to a dense feature. If it's not moving much, we are not converging to anything. We are just stuck there, right? So it makes sense to have, that's the whole idea of Agagrad, right? So it makes sense to have different learning rates for different types of features. And it also makes sense to have different weights at different times. Right? So this is the whole idea, and I hope you got a good sense of this justification for this.